Welcome, everyone. Welcome back to the Geometry and Topology seminar at Durham. So it's a pleasure to present Gabriel Fuhrmann, who just joined the department. And he will talk about amorphic complexity of group actions. So,
yeah, thank you. Thank you for the chance to introduce myself. I mean, I could have done this certainly better if I was able to share my screen. As you can see, I didn't have a live session so far with the students. Everything just pre-recorded video. So this is the first time actually that I speak, mathematically speaking, to actual people at the same time. Okay, and I want to talk about amorphic complexity, and in brackets, I put of group actions. In brackets, well, these are really bold brackets because I will hardly be able to really discuss the case of group actions, and will rather speak about amorphic complexity in general and some of its nice properties. And this is joint work with Mike Kröger, Tobias Jäger, and Dominik Kwitniak, where, in fact, I mean, there are several joint works. So like if I was speaking really about amorphic complexity of group actions, it would really be the four of us. If I just spoke about amorphic complexity, it would be Mike, Tobias, and myself. And what I will actually talk about, most of it is just a joint work with Mike. Okay. And before I really get to amorphic complexity, I want to give an introduction to say two topics, actually. One is topological dynamics, and the other one is fractal geometry. Both introductions will be rather brief, of course, but I need to introduce both topics in order to then be able to say how amorphic complexity bridges between these two subjects. So in most of the talk, I will consider a dynamical system just to be a pair XF, where F is a continuous self-map on X, and X is just a compact metric space. Okay, so of course, then when you speak about group actions, F would have to be a homeomorphism at least, and in general, a topological dynamical system will just be a group action of a topological, continuous group action of a topological group on a compact metric space. But for most of this talk, this is really the setting that we will consider. And then, well, what are the interesting objects whenever we do dynamics? Well, they are the orbits of given points in our space X. And what is the point of the orbit of a point X? Well, it's, in this setting, it's just the image of X under all the iterates of the map F. And now the iterates are just taken in the semigroup N. Okay, and what would be examples? Well, first of all, a very important example is the full shift. By the way, am I audible, and is this legible?
So sometimes you get faint, so I think you may be putting your hand over the microphone.
Okay.
But most of the time you're audible.
Okay, then I go for a less comfortable position because I was sitting in the armchair. Maybe it's better like that. Yes. So okay, so the full shift is, well, our space X is the set of all 0-1 sequences, all one-sided infinite 0-1 sequences, and I will also just denote this by sigma. And our map F here is the left shift, also denoted by small sigma. So the left shift, what does it do? Well, given the point X in the space of all sequences, so this would be something like that. Its image under the left shift is this sequence. Okay, and we won't take a look at the full shift really, but rather on subshift. So what is a subshift? Any closed sigma invariant subset of X, say Y, let's call it Y, any is a closed sigma invariant subset of X, then we call Y a subshift, or also the pair Y equipped with the left shift sigma. This we call a subshift synonymously. Okay, and the goal will be to study certain subshifts by means of amorphic complexity. And before we get there, I have to still introduce a few more things. So on this page, what we see is, say, in a very brief description of say the fundamental objects of topological dynamics on the one hand, and on the other hand, those objects that we will deal with. Still, I haven't really said what our goal is, so let's go for that. Okay, so in dynamics in general, what you do is I defined the notion of orbits here, right? I defined orbits as this, and in dynamics, the goal is kind of to understand how do orbits behave, whatever behave means. For example, do they accumulate somewhere? Where do they spend most of their time, and all these kind of things. And in order to tackle these questions, where there are two things we have to do. One thing is we have to study examples clearly, and the other thing is we have to see how examples that we understand, how they relate to each other. And by relating, I mean the following. So we say a dynamical system XF is an extension of another system of a system YG, which then is also referred to as a factor of the system XF. If the following diagram commutes, so we have our space X, and on this we have our map F acting, and we have our space Y on which the map G is acting, okay? And in between we have the map pi, which is onto and continuous. Okay, so yeah, okay, and the philosophy here is that if we are in such a situation, the map XF or the system XF really is, say, a complicated version of the map of the system YG, in the sense that whatever you see, for example, if in Y you might have a point which is periodic under the action of G. If you have something like this, you may also have a point which is periodic under F, or you may have something way more complicated on top of this periodic orbit. So in this sense, it's really the system XF is really an extension of the system YG, and in this sense, a more complicated version. Unless, of course, the map pi is a homeomorphism. In this case, both systems are considered the same, basically, from a topological perspective. So if pi is a homeo, we call the systems XF and YG conjugates. And yeah, now we are able to formulate the ultimate goal of topological dynamics. Roughly speaking, it is about classifying all topological dynamical systems up to conjugacy. And as in all classification problems in mathematics, what is important if you want to classify something is to introduce, to have certain invariants at hand, invariants under conjugacy. And one such invariant is just Amorphy complexity. And we are not there yet when it comes to describing what this is exactly. But yeah, exactly. But before we get there, I want to become a bit more precise in the description of the systems that we will take a look at. So if you recall, we had as an example of systems, we had subshifts, right? So let's write this notion again here. Subshift sigma was a sigma invariant closed subset of the full shift sigma, which was just this object here. By the way, when I say closed, of course, it takes a topology, and the topology that we consider is always the product topology here on this space sigma. Now, we will not consider just any kind of subshifts, but certain so-called substitutive subshifts. So in order to define them, I have to define what's a substitution. Substitution is a map, say theta, from our alphabet, which in this particular case is 0, 1, into the set of all finite words over this alphabet 0, 1. Okay. So for example, and this will actually be a very special substitution example, which is like the guiding example in all of what I will say in the following, the period doubling substitution. Theta, which maps the letter 0 to the word 0, 1, and the letter 1 to the word 0, 0. Okay. Okay, this is a substitution. I haven't said anything about a subshift so far. Now we are going to take a look at how substitutions define as subshifts. And I won't do this in the most general setting. I will do this for certain kind of substitutions, which the period doubling substitution belongs to, namely for constant length substitutions. With a common prefix. So let's define what all these notions are. So first of all, what is constant length? Constant length just means that the words that I obtain if I apply my substitution to the letter 0 is of the same length, has as many letters as the word that I obtain if I apply the substitution to the letter 1. Okay, this is the case, for example, here in our example, because both letters, letter 0 and letter 1, get mapped to words of length 2. So this is a constant length substitution, the period doubling substitution. Okay, so we have defined this notion, and what we haven't defined yet is a common prefix, but this is, well, easy to anticipate what this will be. Well, this just means the first letter of the two images is the same. So theta of naught is a word whose first letter I will denote with a index 0, and we just want that this letter is the same as the first letter that occurs in the word that I obtain if I apply the substitution to the letter 1. And again, this is exactly the case for our period doubling substitution. If you look here, the first letter in both cases is a 0. Okay, so I've defined substitutions. I've defined constant length substitutions with a common prefix. Now I will show how they give a subshift, how they define a subshift. And in order to see this, well, first observe that, well, our substitution was originally a map theta from 0, 1 into the set of all finite words. Okay, but we clearly can think of it also as a mapping, not from the letters, but actually from the sequences, by applying the substitution individually to every entry of our sequence. So given x in the full shift, we may consider the application of theta on this point x to be the following. Well, what is x? X is a sequence, so it's something x1, x2. And well, now we can just apply straightforwardly our substitution to every of these letters and concatenate the words that we obtain. Okay, so this would be the application of our substitution now, not only on letters, but actually on sequences. Okay, now, if we have not just some substitution, but a substitution with a common prefix, what can we tell about this image of x under theta? So if theta has a common prefix, say, just for the sake of definedness, say a common prefix 0. So the first entry, let's put this maybe here, the first entry of this word is 0, and the first entry of this word is also 0. Okay. Well, then we have that theta x is something which starts with a 0, clearly. Okay, we don't know how it looks further down, but it begins with a 0, clearly. Now, if we apply theta again to what we have there, this is the same as applying it to a sequence which starts with a 0. So what we get is a sequence which now starts with the image of 0 under the map theta. Okay, and now if we assume, and this is an assumption that I haven't mentioned earlier, but if we assume that the length of this word is bigger than 1, so in the case of the constant length substitution, for example, if we assume that every letter is mapped to a word of length 2, like for the period doubling substitution, let me maybe draw this again here, just so you have it in mind. So this was the period doubling, right? So here, every letter is sent to a word of length 2. So if you have this, then we know that, okay, this is here, this is of length 2. If we, and therefore we know, no matter what we started with, which x we started with, after applying the map theta twice, we already know the first 2 letters. And if we apply and apply and apply and again, okay, you see clearly this converges, as we say. Apply theta n times, so this would be this. As we apply theta n times, this converges to a point omega, which is uniquely defined because our map theta is in the topology on our sequence space. It's a contraction where, well, okay, a contraction is only defined properly for metric spaces, but we can, maybe I should, well, I don't specify the metric because it doesn't really play a role. There are thousands of different metrics that you may think of, which topologize our sequence space sigma in exactly the right way, so that we obtain the product topology. And in any of these metrics, this map theta is a contraction. Clearly, the contraction rate depends on the metrics, but this doesn't matter. The Barner fixed point principle gives us that we have a unique fixed point, which I may call omega, a unique limit point of this application, which then is a fixed point, of course, of our substitution. Okay. And now we are at the position to define a subshift associated to our substitution, right? So far we have just defined what's a substitution. We know what subshifts are, but we haven't seen really a subshift. Now, with the substitution, we are given a particular sequence, and with this sequence, we can define the subshift sigma theta to be just the orbit closure of omega under the shift. That is, just to recall, all the shifts of our sequence omega. Okay, and then we take the closure of that. And this is a subshift. It's easy that it's easy to see that it's closed by definition, but that it's invariant, well, it's also not hard, but I won't discuss that. In fact, this is a minimal subshift, where minimality means for all x in our subshifts, we have that the orbit of x is dense in the subshift. Okay, and the goal of this talk would be to discuss on, well, at least to present a result which helps classifying this particular subshift by means of Amorphy Complexity, which I still haven't introduced. So this is the next step. Are there any questions so far? Okay, it doesn't seem to be the case. Then I just proceed. So again, we've defined dynamical systems. We have defined subshifts. Now we define a conjugacy invariant, not only for subshifts, but for, well, on all topological dynamic systems, Amorphic Complexity. Okay. And this is work with Tobias, so with the first two co-authors, Tobias Seeger and Mike Kröger. And myself. Okay. In order to introduce it, we first have to, well, define some notions. So in the following, we always assume we are given a system XF, okay? And then we say 2 points X and Y in X are delta nu separated, where delta is something bigger than 0 and nu is a frequency, so this will be something between 0 and 1. Okay, so we say 2 points are delta nu separated if the following frequency is bigger than nu. So this lim sub n to infinity, we take a frequency, so we divide by n of what? Well, of the number of times that the 2 points x and y are at a distance delta. So the number of L from 0 to n minus 1, such that the distance between x and y, respectively, of their images actually, that this distance is bigger than delta. Okay, and if this distance, if this frequency, which I've written here, the frequency of times at which the points x and y, or the orbits of x and y, are at a distance delta, if this is bigger than nu, then we say x and y are delta nu separated. Okay, I will give this a name. This frequency, I will call it the delta of x and y. It turns, unfortunately, this frequency clearly is also a, say, notion of distance of 2 points, but the point is the distance that we have here is not really a distance in the geometric sense. It's more in the sense of time, because it's a frequency that we compute here really, and this is a bit. It seems to suggest that we can treat this quantity like a metric or pseudometric. Unfortunately, this is usually not the case, but if if, and this, where can I change colors here? Here. If our space X is a subshift, then in fact, this is a pseudometric. So this is important, so I will put it here. If XF is a subshift, we won't see right now why this is of importance, but we will see at the end of the talk. So if XF is a subshift, then d theta is a pseudometric. Okay, so we now have a notion of for 2 points to be separated, and this naturally extends to sets. So we say a set S, a subset of X, is delta nu separated if for all distinct points X and Y in S, we have that these 2 points are delta nu separated, that X and Y are delta nu separated. Okay. Having such a notion, we can define the following number.
What's a pseudometric?
A pseudometric, it's just it can happen that 2 points X and Y, although they are different, are assigned to the value 0.
Okay, thanks.
Okay, so you don't get a house of space with this metric. Okay, so then we introduce the number SEP of X F delta nu to be the supremum over the cardinalities of all these separated sets. So the supremum of the cardinality of S, where S is delta nu separated. And if this number SEP XF delta nu, if this is finite for all delta and nu, which in general it isn't, but if it is finite, we say the system XF has finite separation numbers for obvious reasons. So if for all delta and nu, SEP of is finite, then XF has finite separation numbers. I would like to, I mean, I need a bit more space, obviously, but I don't want to go really over to a completely blank page. Is there a way just to continuously scroll through the pages in Zoom?
I think it's whatever you do on the iPad is what we see.
Yeah, because I can't really. Okay, move this. So, well, take a screenshot, or just keep in mind what I did here, because, well, maybe I should recap this before I change the page. So we have introduced the notion of separation for 2 points, which was this frequency by which these 2 points are at a distance delta. We then said a set is separated in the sense delta nu separated is all its points are mutually delta nu separated. And then we introduced just the separation numbers as the maximal cardinality of delta nu separated sets, okay? And we assume that this number is finite in order to be able to define now the amorphic complexity. So suppose XF has finite separation numbers. Then we define the amorphic complexity as the following quantity. Well, we would like to understand how the separation numbers grow. So this is again the maximal cardinality of a delta nu separated set. Okay. How this grows as we send, first of all, the frequency to 0. So clearly, if we keep delta as it is, but decrease the frequency that we need in order to consider 2 points separated, we will just get more and more separated points. So we take a quotient here somehow with the frequency, and well, not just the quotient, we want, for some reason, we don't know why, but for some reason, it's apparently polynomial growth, which is of importance here. So we take the logarithm of this one and the logarithm of this one and the minus here. Okay, so this gives us the polynomial growth of the separation numbers as we decrease the frequency. And now we just want to get rid of the delta. Take just the supremum of all delta bigger than 0. In other words, the limit for delta to 0. And clearly, there is no, sorry, I should put a limit here. So limit nu to 0. There's no reason to expect that this limit really exists. You, in general, you would have to take the lim sub, lim inf, whatever, but this is really of no importance for this talk. So this is the Amorphy complexity. Okay. It turns out to be a topological invariant, which is always infinite, so meaningless, whenever topological entropy, in case you are familiar with that, whenever topological entropy is finite. But on the other hand, it becomes interesting when topological entropy is 0, which is where topological entropy is of no use. For example, for substitutive subshift, topological entropy is always 0, so it's of no use to distinguish substitutive subshifts. And well, maybe just to at least once come to speak about Amorphic complexity of group actions, just to do this at least once. The say only difference, which then of course introduces a lot of trouble, but still the only difference if you go for group actions instead of this particular setting is you have to find a different way of averaging here. Okay, and the way you would average is, well, you don't assume any groups, you consider amenable groups, and then you average by Ferner sequences, if this tells you something. Okay, and then of course there are natural questions like, is it independent of the Ferner sequence, etc., etc. And we can answer these questions, but I don't think, no, I know for sure I won't get there today. So, okay, this is all almost all that I will have to say about Amorphic complexity of group actions for today. So let's go back let's recap what we did so far. We introduced substitutive subshifts. We introduced Amorphic complexity, and I haven't said any word so far how to how to compute Amorphic complexity. But before we actually get there, I will just introduce yet something else, namely, well, the box dimension. So this is, if you want now, a new introduction to a different topic, fractal geometry. Well, what does fractal geometry do? Basically, in fractal geometry, you classify sets in terms of their size, in a certain sense, where size is whatever notion of dimension. And there are thousands of different dimensions around, but the one which is important for our talk is the box dimension. So, sorry, given a compact metric space X, we define the box dimension as the following expression. Let me first write it down. So what is this? Well, the most important thing here is n epsilon of b. N epsilon of b is the minimal number of sets of diameter less than epsilon the minimal number of sets B should be X. Sorry, yeah, exactly. Thanks. N epsilon of X is the minimal number of sets of diameter less than epsilon that it takes to cover the set X. Okay, now if we take again the logarithms and divide this stuff and send epsilon to 0, what we compute here is actually the polynomial growth of the number of sets of size epsilon that it takes to cover the set X as we send the diameter to 0. Okay, so this is the box dimension. And again, it's not clear and in general not true why this limit should exist. And you can take lim inf, lim sub. This gives you the upper and the lower box dimension, but this I don't want to worry about in this talk. Okay, and essentially you can take any compact metric space and compute the dimensions, but there are particularly nice ones which are defined through so-called iterated function systems. Iterated function system, so abbreviated by IFS. And this is nothing but a collection of finitely many contractions on the space X. So this is nothing but the set F1, say to Fn, where each Fi is a contraction. Okay. Now contractions have fixed points clearly on a complete metric space. And similarly, the following map has a fixed point. So we may define a map capital F on the set of all compact subsets to itself by sending a set K to the union I equal 1 to N Fi of K. Okay. So since the maps Fi are contractions, it's not hard to see. I won't do this again, but it's not hard to see that this map capital F also is a contraction in which space? Well, in the space of compact subsets of X equipped with a Hausdorff metric. Now, again, every contraction on a compact metric space, on a complete metric space, has a unique fixed point, and this fixed point so therefore there is a unique compact subset, say A of X, such that f of A equals A. And what was f of A again? Well, this was just the union over all I Fi of A, okay. And this set is also referred to as the attractor. Of the IFS. Okay, good. An example, maybe, just that you see this is not completely empty what I'm talking about here. Well, the middle field Cantor set, which every one of you knows, I guess. Is the attractor of the map X gets mapped to 1 over 3X, and the map X gets mapped to 2 over 3 plus 1 over 3X. Okay, now, without getting into the details, still, the nice thing of this equation here, which defines our attractor, is that on the right-hand side, we have a covering, right? We have a covering of our set A. And discovering is by set of diameter, well, contraction rate of A, of Fi times diameter of A. And if we apply F and again and again and again and again, well, we get, well, some powers of our contraction rates. That is, we get finer and finer partitions of our set A. And this helps to compute the box dimension of this attractor. And there is a simple formula for the box dimension, which a priori is only an inequality given by the number of elements of our partition, which is just, well, how often do I apply the map F? Sorry, how many maps do I have? Yeah, how many maps Fi do I have? So this was n, to the number of iterations of my map capital F, so n to the L, say, over the size of these sets, which was given by CIL here. So let's say CI is less or equal C. So we take, say, the maximum or the weakest of these contractions. So we have a C to the L here, okay, and send L to infinity, just to get that an upper bound for the box dimension of an attractor is given by the logarithm of the number of elements in our IFS over the logarithm of the contraction rates of these elements. And in general, first of all, if this is a bit confusing to you, I agree, I didn't really specify every detail here, but I lost a bit time because I wanted to use some slides at the beginning, so I cannot get too specific here. So don't worry about this, and just maybe take it for granted that given an iterated function system with n elements, so this is one ingredient, and contraction rates C, we can compute the box dimension, or at least an upper bound of the box dimension, by means of this equation. And well, in general, it's just an upper bound, but if up here in this definition of our attractor, we not only have a union, but a disjoint union. And if further, the contraction rates Ci, if all of them coincide, in fact, with a C, and if moreover, this is not just, say, some Lipschitz constant, but if in fact we have for each map Fi that it's a similarity, that is, we have d of Fix, Fiy equals C times d of x and y. So it's not just less or equal than C times dxy, it's equal to that. In that case, we actually get an equality here. Okay. Good. That's it for, say, the fractal geometry parts of this talk. And now I would like to briefly discuss the results. First of all, and maybe I would like to cheat here a bit, so take a look at my slides. First of all, recall that we had if xf is a subshift, then this quantity d delta xy is a pseudometric, right? This was, if you recall earlier, we defined the notion of 2 points xy being delta nu separated, and this was this asymptotic frequency of separation between the 2 points x and y, and this asymptotic frequency d delta xy is a pseudometric if our space X is a subshift. So what we can do, we can quotient out, like identify those points which are identified by this pseudometric, okay? And here's the first theorem. This is with Mike. and myself. The first theorem is that the amorphic complexity, also say, suppose our system, our subshift X sigma has finite separation numbers, so we could define the amorphic complexity. Then, first of all, this metric d delta, it doesn't really depend on that, on the metric that we put on the space X, okay? As long as it generates the right topology, it gives us basically the same metric. Of course, it's not exactly the same, but Lipschitz equivalent metrics, which is always from the perspective of geometry or fractal geometry, it doesn't make any difference. So then d delta is independent of the metric on X and independent of the particular delta, okay? And second, the amorphic complexity of our subshift coincides with the box dimension of this space X d delta. Okay, and now, and this will be the last statement, and for this I have to cheat, otherwise I get the expression wrong. Okay, so this statement says that if you are given a subshift, as long as we can compute the amorphic complexity, it coincides actually with the box dimension of this factor space X d delta. Okay, and here is the last theorem. This is again with Mike. So suppose we are given a substitution with a common prefix and of constant length. Those were the kind of substitutions, for example, like this one, the period doubling. The substitutions for which we could easily define an associated subshift. Suppose we are in this situation, then unless our subshift is trivial, the amorphic complexity of X sigma is given by the logarithm of the length of the word, say, theta of naught, over the logarithm of theta over theta star. And just 30 more seconds. What is this what we have here? Well, this here is a contraction rate. This is the contraction rate of our substitution, just not on the original space, because on the original space the contraction rate really depended on the metric that we started with, but on this quotient space it doesn't anymore. So this is the contraction rate of our substitution, and this here, this is just the number of elements of an IFS, which is given by theta, and then we apply, so theta, then the shift after applying theta, etc., until length of theta minus 1 times the shift after theta. So in other words, on this quotient space, our substitution defines as naturally an iterated function system whose attractor is exactly the quotient of our subshift, and therefore we can define compute the amorphic complexity by this formula. And now I'm done. Yeah, thank you for your attention.